Hello, my name is Raul Cornejo, and this is a video for lab activity number 7 for class EEE3303 lab. And here's the results I got written down. Activity 7 part 1 is another common emitter transistor. So when the voltage at the collector emitter junction is 6.3 volts and the base current is 1.94 milliamps, the configuration I had was the DC power supply was 10 volts. The function generator had a sine wave of 5 volts peak to peak. The base resistor was 175 kilo ohms. The emitter resistor was 1 kilo ohm. The low resistor was 1 kilo ohm, and then the base current was 10 microamps. So that leaves a beta of 177.9, which is operating range of the transistor. The typical beta for a 23904 transistor, which is used for the whole experiment, is 100 to 300. So it's in good operating range. And then the capacitor 1 was 0.003 microfarads. Capacitor 2 was 1 microfarad in order to coupling capacitor that filters out the low frequencies and amplifies the mid to high frequencies. Here is the multi-sim result, and we get a current of 2.139 milliamps at the collector, and the emitter collector junction voltage is of 5.713 volts. So as you can see, the input frequency at 100 hertz, very almost no amplification, both are very small. It's got 139.45 to 2.3 millivolts. This is 1.36. That here 500 hertz starts to increase the amplification. With the measure results is a voltage gain of 2.25, and at 1 kilohertz you can see that the output is actually increasing much more now. The sine wave is more visible. The input's still a bit low. 1.941 volts peak to peak over 1.027 volts peak to peak for the input, and 1.89 amplification. Now when it gets to 5 kilohertz, is a really big amplification now. With the voltage, so the voltage gain is at 4.98, almost 5, and at 10 kilohertz, once again, it just keeps increasing the amplification. But also another effect is that the signal is beginning to get clipped off. The amplified voltage output could be much greater, but is limited by VCC of 10 volts DC, since the transistor amplifier is unable to provide a higher output voltage than the voltage it is being powered by. So it's just capped by 6.42, not volts, it's 6.42 voltage gain. The output voltage was 9.354 volts, input was 1.457 volts. And once again, it's still capped off around a value of 9, almost 10, and then it just gets more distorted with the input frequency of 20 kilohertz. So our input signal is increasing as it reaches higher frequencies. However, the distortion of the output signal increases. Output signal is still capped. So output signal is capped at 9.645 volts, and the inputs increased to 2.042 volts. So it's a 4.72 gain. Much less than this one, the 6. Here's the picture of the circuit that was used. Here's a 0.003 microfarad capacitor and 1 microfarad capacitor at the emitter. And this is all the resistance that's used. A couple of resistance to obtain that value for 175 kilo. Now for part 2, it's a emitter follower configuration, in this case for the transistor. So when the collector emitter junction is at 5.94 volts and the collector current is at 2.06 milliamps, the DC is once again 10 volts, but had to lower the sine wave to 1 volt peak to peak. Here the base resistor 400 kilo ohm, the emitter resistor 2 kilo ohm, and the base current is 20 microamps. So beta is 103. Coupling capacitor is 0.003 microfarads again, in order to filter other frequencies and amplify mid to high frequencies. And here are the results for multisim, which are very similar to the measured values. So here 100 hertz, inputs at 1 volt, but there's no, I mean, it barely knows, there's no signal visible. There's a 0.025 voltage gain, so it's way less. 500 hertz, voltage gain here is 0.12, still low. 1 kilohertz is just 0.23. 5 kilohertz is much more now. The output, so it's a voltage gain of 0.74. And then 10 kilohertz is very close to 0.89, so they're much closer now in value, the input and the output. 15 kilohertz, 0.92, it's increasing. And finally at 20 kilohertz, voltage output is at 0.95. So I wrote that an optimal emitter follower optimal emitter follower will have voltage output that is equal to the voltage input because of the way the transistor works in the emitter follower. In the measured result, the output voltage operating frequency is slightly lower than the input voltage. This is expected behavior for an emitter follower transistor. And here's the circuit. And then this is a common base, which I also got here right now, still set up. Okay, collector emitter junction 6.13 volts. Collector current is 1.75 milliamps. This once again is a 10 volts of DC power supply. At sound waves of 1 volt peak to peak. Base resistors 500 kilo ohm R1, which would have been right here. The actual lab handle was 1.5K. And the collector resistor is of 170 ohms. In this case, instead of measuring the base current, is the emitter current that's measured. This is a 1.62 milliamp. So you just got an alpha, which is a carrying gain of 1.08. While in our common base configuration, the carrying gain alpha will be close to unity. You can see it's slightly above. Measure social calculations close to unity in the circuit. Shows alpha close to unity in the circuit. As well in the multi-sim as well. Similar results. So once again here, input frequency 100 hertz, voltage gain of 0.56, 100 hertz frequency. Input is a voltage gain of 1.03. It's increasing much more now as that's reached 1 kilohertz, so 1.54. 5 kilohertz is at 3.41, but as notice there's a distortion beginning to occur at this point. And at 10 kilohertz, and it increases the voltage gain up to 5.07, but again it's clipped off. 15 kilohertz, distortion increases much more, and the voltage gain increased to 6.94. Finally, at 20 kilohertz, it's a voltage gain of 7.024. So a common base emitter is capable of being used as a voltage amplifier. It is not ideal to use for power amplification since the input and output current are identical. And as observe, the signal output starts getting distorted around 5 kilohertz, but amplitude is still increasing. And that's the end of the video. Sorry for being so long. Bye.